So, good morning, good evening, good afternoon. Take my greetings according to your timing. I know everyone is in too much pressure and exams are knocking at the door. Meanwhile, I am recording this lecture at 1:35. You can see in my screen recording. So, let's wrap up our module 2, that is our spectroscopic techniques and applications. And this video is the first part of a 7-part series where we will master the fundamentals of how light interacts with matter. If you have ever wondered how scientists can look at a chemical sample and tell exactly what its structures look like just by shining light on it, this is the video for you. To let's dive into this topic with more enthusiasm, and actually this lecture will be completely MAKAUT based because we are focusing the semester. So without further delay, let's come to the first part of this series of spectroscopy. So first let's move to the definition part. So this is the definition you could see. So first, simply we can say that it is the branch of science that studies how electromagnetic radiation interacts with matter. Okay, so the pattern of absorbed, emitted or scattered radiation gives a fingerprint of the molecular structure, energy levels and dynamics of the sample. So I mean to say that the pattern we get from this interaction acts like the fingerprint of the molecular structure, energy levels and dynamics. Just like no two human beings have the same fingerprint, no two molecules give the exact same spectrum. So this is the overall definition view of the spectroscopy. After this, let's move to the electromagnetic radiation and quantum nature. So, electromagnetic radiation behaves both as wave as well as a stream of photons. As a wave, it is described by frequency mu, wavelength lambda and wave number nu bar. As a particle, it is like photon carries a discrete amount of energy is equals to h nu. So, I mean to say that when wave nature is there, we say about frequency, wavelength and wave number. But when it comes to particle, we say that light travels as a stream of packets called photons, where each photon carries a certain specific packet of energy given by Planck's equation is equals to h nu. Okay, and now come to the remembering part of the module. So this is the important formula part because actually teachers love the conversion. So through this you can expect a conversion where you can see that c is equals to speed of light is equals to what? Nu into lambda. Okay, and here wave number is equals to 1 by lambda and then nu by c. Okay, and E is equals to h nu, hc by lambda is equals to hc nu bar. So here you can see completely how they are correlated to each other. So this is the very important equation. I'm marking this as important. Go through it once. Okay, so let's not waste any more time. Let's get into another things. And here you can see that two things more important. So remember the speed of light is in meter per second. Okay, here is Planck constant. When you are taking the power as 10 to the power minus 34, then joule seconds, and then lambda is in meter and nu is in hertz and wave number is in centimeter inverse when lambda is in centimeter. Okay, now the electromagnetic spectrum and spectroscopic reasons. This is a very basic part, that's why I'm not going into too deep. So now why do we have different types of spectroscopy? So see, because different regions of electromagnetic spectrum have different amount of energy which match different types of gaps inside a molecule. As we go from radio waves to gamma rays, the energy increases subsequently. Therefore, you can see the whole spectrum over here, and I am going through this region energy mapping. Here you can see this beautiful table over here, where radio wave is there with very low energy. Okay, but wavelength is one of the longest. Okay, 1 meter to 10 kilometers. So the type of transition is nuclear spin flip is there, NMR and MRI can also be there. Then microwave is First there is radio wave, then there is micro, there is infrared, visible, ultraviolet, X-ray and gamma rays. Subsequently we will be visiting each and everything one by one, but as we are having very few time left with us, so we will be carry forward this session with bit enthew and fast forward mode. Let's get into the next part. Okay, so the three photon matter events. Okay, that means our absorption, emission and scattering. Fine. When a photon meets a molecule, three main things can happen. Okay, what are the three main things? Absorption, emission and scattering. Through this you can clearly understand what it is. So absorption, when there is some photon over here, they absorb certain amount of energy, then they move to their next state, that is called our absorption. Okay, what is emission? Already there is some there is a photon in some energy level, it loses its energy and come back to its ground stage, or you can say the lower level, so that is called your emission. Okay, then what is your scattering? Scattering means simply the photon hits the molecule. Okay, and then it is instantly redirected to bound off at an angle with or without changing its energy. So this is called as scattering. Scattering is also known as Raman scattering. Okay, I'm writing it, just you can just mention it in your notes as well. So here you can see what is this quick comparison is there between absorption, emission and scattering, where so absorption means photon raises molecules from low to high state. In emission, excited molecules drops back releasing photons. Photons redirected or without energy change. Okay. So in absorption, loss of intensity at frequency, that new light at characteristics its frequency, and then in scattering, light at angle from beam. Okay, for example, absorption is seen in UV visible region, or you can say infrared region. Emission could be seen in fluorescence and AES, and scattering simply Raman scattering. Okay, you can say X-ray scattering is also there, no doubt. And then after that you can see